Hi, welcome once again to Math as a Second Language, where today we're going to talk a little bit about what happens beyond place value. And just to sort of catch up with what we did last time, we talked about the chronicle of human endeavor, how you go along smoothly at a certain plateau, you hit an obstacle, and you either stagnate where you are or you overcome that obstacle, move to the next plateau, and from that plateau you get a better view of what was happening below. But by the same token, you get the bad news that there are other obstacles ahead. And so we went through this starting at the plateau of hieroglyphics, pictures on the walls of a cave. And in our last lecture, we culminated our journey by showing how place value developed. And I hope that you noticed as we went along the way what we mean when we say that innovations don't take place in a vacuum. What happened is that each level inherited a legacy from the previous level, and in turn left a legacy for the future level. So now here we are at this new plateau called place value, and all of a sudden we realize that although this was a great accomplishment, there's another obstacle ahead. And what that obstacle is that now because of place value, we can write numbers that are so large that they require, as we mentioned last time, Avogadro's number, a 6 followed by 23 zeros. There are now as many zeros that we have to keep track of as there were tally marks when we went from hieroglyphics to tally marks. In other words, it's that old adage about no matter how much things change, they somehow always remain the same. So today we're going to take a look at what happens beyond place value. Let's just take an example. If we were talking about tally marks right now, and we talked about the number 23,456, we say something like, wow, that would be a lot of tally marks, but imagine how nice this is in cutting down on how many tally marks we had to use. Well, now what happens if instead of having 23,456 tally marks, we had a 1 followed by 23,556 zeros? I mean, that dwarfs Avogadro's number. And somebody might say, well, you're never going to have to deal with a number that big. Well, I'm positive at the time of Avogadro, people were saying things, who's ever going to dream of a number that big? You see, we never know when we've reached the final plateau or when we're just heading for another obstacle. So the point remained, we wanted to find a better way, a more compact way, a more reasonable way to do arithmetic when you were dealing with numbers as large as a 6 followed by 23 zeros. So what we do is, let's start with a little question. If I said to you, how much is 3 2s? I can imagine on the preschool level, a youngster saying, well, at the school, I was going to say at the preschool level, it'd be even easier. At the preschool level, the youngster might just say it's 222, 222. Usually, when an adult hears the question, how much is 3 2s? They put in the words tacitly the sum of 3 2s. If I say how much is 3 2s, you say 2 plus 2 plus 2. But there are times when you might want to multiply 3 2s. We'll talk more about that later in the course when we go into this in more detail. But for the time being, let's show how this applies to extending place value. What we're going to do is we're going to invent a new notation that when we're talking about the product of 3 2s, 2 times 2 times 2, we're going to write that as 2 to the third power, a 2 with a little 3 above it. We're going to read it as 2 raised to the third power, or simply 2 to the third power. And 3 is referred to as the exponent, and 2 is referred to as the base. Now, it's very easy to become confused when you first learn about exponents. For example, there's no danger if you meant to take 2 3s and by mistake you took 3 2s. In other words, 2 times 3 is numerically equal to 3 times 2. That was our commutative property of multiplication. But 2 to the third power is not the same as 3 to the second power. In other words, when you interchange the base and the exponent, look what happens. 2 to the third power means what? 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. Not 6. Many people look at this and they say, oh, 2 to the third power, that must be 6. No, if you say 6, you're confusing it with 2 times 3. On the other hand, 3 to the second power means what? The product of 2 3s. 3 times 3 is 9. 8 and 9 are different numbers. They're not the same thing. Now, it's very, very cumbersome to deal with exponents. Let me give you an example. If we're dealing with 7 times 10, well, you can rewrite it as 10 times 7 as you want. You can very quickly annex a 0 and say that the answer is 70. But when you're dealing with 7 to the 10th power, look what's happening. This says multiply 10 factors of 7. Well, this is what it looks like written out. 7 times 7 is 49, so we still have this to do. 49 times 7 is 343. We still have to multiply that by 7, multiply the result by 7, multiply that result by 7, multiply that result by 7. I think you're starting to get my drift a little bit. Multiply that by 7, multiply that by 7, multiply that by 7. My golly, that can be very tedious. And the way we get around that is our exponential notation. We simply write it as we said, 7 to the 10th power. And on our calculator, we find a key. On most calculators, it looks like this. Not all calculators are alike. What this tells you to do is put in a number, press this key, then write down what exponent you want, hit the equal sign, and the answer will appear. In other words, using the calculator, I punch in the 7, hit the X to the Y key, punch in 10, 10, hit the equals button, and lo and behold, almost instantly comes up the number 282,475,249, which is quite a labor-saving device. And by the way, let me just throw in a word here about the use of calculators. People talk about calculators don't help you think, etc. Well, maybe that's true. In fact, it is true. What they do help you do, however, is to avoid cumbersome computations. You see, what the calculator will do for you is it will raise 7 to the 10th power very, very quickly, no sweat. What it won't do for you is to tell you that you wanted to raise 7 to the 10th power. In other words, even using a calculator, you can punch in the right numbers, but it's for the wrong problem. Or you can inadvertently make a typo, in which case it's a good idea to have a number sense as to what your answer is supposed to be before you use the calculator. So it's not a case of whether the calculator is good or bad. It's a case of the calculator has a purpose. And as long as you use it for that purpose, things are fine. It's sort of the same as a word processor. It'll catch your spelling mistakes. It'll help you cut and paste and what have you, but it won't give you clearer thoughts. It will cut and paste whatever you give it to cut and paste. So I just wanted to interject that for the time being. But now that you've seen how tedious it might be to raise a number to a power, let's look at some cases where it's not that tedious. For example, what would 0 to the 4th power mean? It would mean 0 times 0 times 0 times 0. Any product of zeros is 0. So the way we say that is if n is any whole number other than 0, 0 to the nth power will always be 0. And the similar thing happens with 1. For example, 1 to the 4th power is 1 times 1, which is still 1, times 1, which is still 1, times 1, which is still 1, and the answer is 1. In other words, if n again is any non-zero whole number, 1 to the nth power is just equal to 1. But these are kind of trivial. I mean, what good is it to know that any product of zeros is 0 and any product of 1s is 1? Isn't there another number that can be more useful that is easy for us to use? And it turns out that 10 has that property. Let's take a look. Let's look at 10 to the 4th. What does it mean? 10 times 10 times 10 times 10. Well, 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. Now notice what happened. I outlined this in a different color. Notice that the exponent is 4, and the answer is a 1 followed by 4 zeros. In other words, to generalize this, I think you can see the pattern now. For any non-zero whole number n, 10 to the nth power is a 1 followed by n zeros. Not a 10 followed by n zeros, a 1 followed by n zeros. So knowing that, we can now look at Avogadro's number in a different way. Recall what Avogadro's number was. It was a 6 followed by 23 zeros. Now, that's the same as what? A 6 multiplied. See, in other words, it's 6 of these guys. It's 6 times whatever this number is. But what is this number? It's a 1 followed by 23 zeros. And how do we agree to write that? A 1 followed by 23 zeros is 10 to the 23rd power. So a much more convenient way of expressing Avogadro's number is to say it's 6 times 10 to the 23rd power. In the same way that place value allowed us to take the place of many, many tally marks, exponential notation allows you to take the place of many, many zeros, and in fact tells you at a glance the magnitude of the number. In other words, if I'm looking at 23 zeros and instead somebody else is looking at 26 zeros, it's pretty hard to tell the difference by looking at what's between 23 zeros and 26 zeros. But if you look at 10 to the 23rd and you look at 10 to the 26th, right away you see that 10 to the 26th has 3 more zeros. It's 1,000 times bigger than 10 to the 23rd power. And the hardest thing to do here is to try to get a mindset that when you write 10 to the 6th, that is as much a noun as writing million, writing a 3 followed by a 1 followed by 6 zeros, etc. In other words, when we talked about 3 plus 2 is 5, only when 3, 2, and 5 are modifying the same noun. See what's happening here? 3 million plus 2 million, the common noun is million, so the answer is 5 million. What is this? This is the place value way of rewriting this. In place value language, a million is represented by 6 zeros. So this says 3 million plus 2 million is 5 million. Now you look at this, and I'm going to highlight this a little so you see what's really happening here. And you say, well, I'm not used to this guy. Well, it doesn't matter. You have 3 of these and 2 more of these. How many do you have altogether? You have 5 of them. In other words, in the same way that 3 is an adjective modifying million here, it's an adjective here modifying 10 to the 6th. You have 3 of these guys, 2 more of these guys, that's 5 of these guys, okay? So I think that's enough for today's lesson. So let's come to what we ordinarily do and talk about our practice problem. Remember what that is? We're going to end each lesson with a problem for you to work on your own. You're going to read the problem, pause the video so that you see what, you can study the problem. And after you've worked on the problem, or even if you don't want to work on it and just see what we did and why we did it, etc., just resume watching the video. The practice problem is to write the sum 3 times 10 to the 6th plus 2 times 10 to the 5th as an equivalent place value numeral. In other words, what would this number look like if you wrote it in the language of place value? Okay? Well, now that you've had enough time to look at the problem, let's just write what these numbers mean. The 3 is modifying 10 to the 6th. 10 to the 6th is a 1 followed by 6 zeros. So this is a 3 followed by 6 zeros. 10 to the 5th is a 1 followed by 5 zeros, and 2 is modifying that. So 2 times 10 to the 5th is a 2 followed by 5 zeros. So if we want to add these two numbers, and what was the purpose of this problem? Could be a lot of things you could think of. The idea was what? The only time you add 3 and 2 to get 5 is when 3 and 2 and 5 are modifying the same noun. Here the 3 is modifying 10 to the 6th. Here the 2 is modifying 10 to the 5th. And so we can't add the 3 and the 2 here. And notice the funny little sequence that you might want to think about. Here was the 3 here and the 2 here. And when we added them, they sort of added this way. But anyway, what we wanted to show for today was this new language. We are going to study exponents in detail towards the end of our course, because they're very, very important. Far more important than just using them in place value. But remember what we said, everything is a plateau we get to an obstacle, we're not going to rush from step 1 to step 20, and because if we did, things would be the same mess that they're usually in when we try to memorize things and leave steps out. Just concentrate on this. We'll return next time and actually start the arithmetic of whole numbers using the adjective noun theme as the basis for it. But until next time, have fun, study hard, and I'll be looking forward to seeing you. Take care now.